Let's try an example where we're finding the moment of inertia using integrals. Here we have a uniform solid cylinder with radius capital R, mass capital M, and length capital L, and we want to find its moment of inertia about its central axis. So you'll see that I drew in the z-axis here. That's what we would be rotating around and finding the moment of inertia around. Now remember, we found that the equation for the moment of inertia as an integral is the integral of r squared dm. But remember, the problem here is that r squared and dm don't match in terms of the variables. So we want to find the connection between a position and a mass, and we can start with density. So we rewrote this knowing that density is a mass per volume, and we can look at a little tiny bit of mass and a bit of volume by really looking at maybe a cylindrical shell. So we kind of took just a shell of this cylinder and kind of imagine sort of pulling that all the way down. It would have some new radius, little r. It would have some little thickness, which would be like a dr. We can now rewrite dm as the density rho times this little bit of volume of that cylindrical shell. That would mean that our equation now becomes the integral of r squared times rho dv. But what exactly is dv? What is that bit of volume? Remember, it's this cylindrical shell that we've pulled out of here. So that little bit of volume would be equal to the circumference of that little shell, so a 2 pi r, multiplied by the length of the shell times the thickness, which would be that dr. And now we can rewrite our integral as our r squared rho, where dv is 2 pi r L dr. And finally, we have variables that match up, r's and a dr. Anything that is a constant could be pulled outside of the integral. So our 2 pi can come outside, our rho, the L can come outside, and now we're integrating. There's 2 r's here and another one there, so we're integrating an r to the third dr. And we would do this integral from 0 to all the way out to the edge of the cylinder, which is all the way out to capital R. Now, if we were to just look at the integral part of this, integrating r to the third dr would simply become r to the fourth over 4. And really, that would be a lowercase r for right now. So we would have our r to the fourth over 4 and then evaluate from 0 to capital R. Now plugging in capital R, you would get capital R to the fourth over 4, and then plugging in 0, you would just get a big 0. So we can write our equation now as the 2 pi rho L multiplied by r to the fourth over 4. We could simplify this even further, however, because rho was not actually a variable that was given in our equation. So we should replace rho with what rho actually is, which is a total mass per total volume. Now the total volume of a cylinder would be a pi r squared multiplied by the length or the height of that cylinder. So coming back to our equation, we'd have our 2 pi times the total mass divided by a pi r squared L, our L up here, and then our r to the fourth over 4. Now we can do some simplification. We see that this 2 and that 4 could simplify, the pi's would cancel out, the L's would cancel out, 2 of these r's would cancel with 2 of those, and ultimately what we would be left with would be our 1/2. We'd have a big capital M still in there, and we would have an r squared left in there as our final answer. Now, like I said in the screencast for section 10.4, you can look on page 300 for the moment of inertia of some simple shapes, and you'd find that for a solid cylinder rotated about its center, the moment of inertia is 1/2 mr squared. So it's nice to know that those equations are there for you, and you won't always have to do all of this work to get the moment of inertia of a simple shape.